In this video, we're going to look at how we can apply the equations that we used for speed of waves and look specifically at problems that deal with those equations for sound. Of course, sound is a type of wave, and so any equation we use for waves we'll also be able to use for sound. So the two equations we used in the last unit are, of course, your DirectTV equation, which we used a lot last semester. And the DirectTV can also be put into the triangle, which is where DirectTV comes from, where you have D at the top, and then you have TV at the bottom. So DirectTV. The other one is the equation specific to waves, which is V equals lambda F, where V is your speed, lambda is your wavelength, which is just the length of one oscillation, and F is your frequency, which is how often those waves come through. Now we did have another version of this equation, which was V equals lambda over capital T, and that's because of the inverse relationship between frequency and period. So here T is your period. That's the length of time for one oscillation. So this equation is really just DirectTV. V equals a type of D over a type of T. So our first example is going to use DirectTV. How do you know? It's depending on if it tells you to find wavelength, frequency, and period, or if it just gives you a distance and time. So this is sonar. Sonar is what boats use to figure out how deep the water is underneath them. We use this for mapping the ocean floor, as well as just figuring out military-wise if there are submarines or anything like that. So sonar is a method to use to determine the depths of the ocean. And how it works is that you have water, and you have the ocean bottom, and our boat sends out a signal. And the signal goes down to the ocean bottom and back up. So in this example, if this takes 2 seconds and we have a speed in the water of 1450 meters per second, notice this is much faster than in air, then we're trying to figure out how deep the ocean is in this particular location. So this one is a DirectTV problem. So V equals D over T. Now, since it's 2 seconds down and back, then one direction is going to be 1 second. So to find our time, we're just going to divide by 2, which gives us 1 second. So V is 1450. We're looking for D, and T is 1 second. So we're going to multiply 1 over. We get a D of 1,450 meters. So actually not very deep. Our second example is now going to use our other equation because it specifically says in it frequency, and we're looking for wavelength. So wavelength, frequency means we have to use the other equation, V equals lambda F. So we're given the frequency of 256, so we're going to plug that in for F, and we're given the speed of 343. Notice, yes, definitely in air, sound is much slower than in water. So then we're solving for lambda. So again, it's just going to be a simple division problem. So 343 divided by 256 gives us a wavelength of 1.3398. Now for WebAssigned 1.34 would be just fine, but you know, it doesn't hurt to put a couple more digits in there just in case. So one thing to think about is sound waves, a lot of them can have really long wavelengths. So middle C, if you play piano, middle C is the very middle of the piano, hence middle C. And so that has a wavelength of 1.34 meters. This is why the string inside the piano has to be so long, is because it has to be able to vibrate at a frequency to create a wavelength of such a long wave. 1.34 is about 1 1/3 meter sticks. So middle C string is usually about that long. All right.